Okay, let's get started. So welcome everyone to another lecture as part of our ID 5130 parallel scientific computing course. Okay, so with the last lecture we kind of finished our programming in MPI chapter. We would now start a new chapter today, that is numerical methods using MPI. So this is the fifth chapter in the syllabus, and we're going to look at pretty much the same numerical methods that we discussed in the context of OpenMP, and only difference is that now we are going to use MPI to basically go over these methods. Okay, so some of the essentially the introduction and how the methods work and those things would be straightforward, so they will not be repeated again in MPI. Rather, we will kind of focus on essentially distributed memory implementation. Okay, distributed memory implementation of these numerical methods. Okay, because that is what you would use in the context of MPI. Okay, fine. So if we kind of start off with the numerical methods, the first one is of course the trapezoidal rule for the numerical integration, which we have already discussed, right? Which we already discussed, so we don't have to do it again. So essentially for today's lecture, I'm going to kind of go through the matrix addition as well as matrix multiplication, and depending on the time, we'll also kind of get started with explicit finite differences or finite difference schemes. Okay, so alright, so as we have already covered the trapezoidal rule, let us get started with matrix addition. Okay, so matrix addition is kind of quite simple, whether it is in the context of shared memory or in the context of distributed memory. So if we have, let's say, two matrices, let's for the sake of simplicity, let me assume we have two square matrices of size a n by n and b n by n, and if we were to add it, we just have to add an element by element and then obtain what are the values in the final matrix, that is C matrix, right? So this is basically going to be C of ij equals your A of ij plus B of ij. Alright, so this is kind of very simple and straightforward, because all we have to do is basically we just have to add these elements, right, one by one, and then this is basically simple because we just have to use the same decomposition, right, or what we call it as partitioning, right, of the matrices. The same decomposition or partitioning of the matrices essentially across all A, B, C, right, all A, B and C, right. Once we kind of ensure that this is the same partitioning that is done, then we can easily accomplish this task. So for example, let us say if we have a row wise block decomposition, that means what we're going to do is we're going to assign decompose A and B, say we would like to add them and obtain the C matrix, and the way we're going to do it is we're going to assign let us say same number of rows for A, B, C will be assigned to the same processor, right? For example, let's say these colors here represent a set of few rows here, so let's say each color here represents maybe 5 rows or 10 rows depending on how many we consider. So we just use the same decomposition everywhere, and then so let's say this is probably 5 rows is represented using this color here. Okay, so as long as we use the same decomposition for all the ABC, we can easily add element by element and then basically obtain the final matrix. Now this is what I have shown here is known as a one-dimensional decomposition. Right, now we could also go for essentially two-dimensional decomposition, in which, or even a column-wise decomposition, or a two-dimensional decomposition, in which you basically have kind of blocks of matrices will be assigned, and each block would be assigned to a single process. So no matter whatever you kind of decide, matrix addition would be very straightforward. Okay, whether you have a 1D decomposition or a column-wise decomposition or a square decomposition, right? If you have basically a two-dimensional also, this works perfectly fine, right? Okay, so if we also a little bit discuss about this, essentially once you kind of decompose, the computations, I mean essentially the addition of the matrices per se do not require any communication, right? The only communication that is required is in the initial broadcast of the matrix rows, right? Or instead of calling it as broadcast, it's basically kind of a scatter, right? Initial scatter of the matrix rows to different processes, right? That is the only communication we would need. And then once the summation is done, then you probably have to kind of collate all the rows onto the process 0, right, which would basically call for an operation similar to gather. Okay, so that's all is the communication that is required, but the computations per se actually do not require any communication. So this is one of the simplest things that we can do, is basically the matrix addition. Okay, fine. So with that, I would kind of now go to the second thing, that is basically the second numerical method we would like to discuss today, that is the matrix multiplication. Okay, so let us look at matrix multiplication. So matrix multiplication is actually much more involved compared to matrix addition. So again, we assume that we have two square matrices. We have A n by n, B n by n, which we would like to multiply and then obtain C n by n. Okay, so what we of course recall is that from our elementary linear algebra course is that if we have two matrices A and B, the way you would multiply is essentially multiply one row of A, right, with one column of B, and then you would basically obtain one element, right? And then similarly you would multiply with another column of B and then obtain another element, another column, and so on, and then obtain elements here, right? So to get one row of C, you have to basically take one row of A and multiply all the columns of B, right? So one row of A and one row of A and all columns of B are required to compute one row of C, right? So essentially that is the idea here. Now how can we go about doing this thing? So this in this one, whatever we discussed in the context of matrix addition doesn't work, because if you decompose them based on rows here, right, then this doesn't work, right, because it requires all the elements. So in order to get one row here, you have to kind of have the entire matrix B for every row. As a result, the same decomposition that we have used for matrix addition is not going to work. So but what we can do is, if you have, of course, so method one is basically if you have small matrices, right, if you have small matrices, then we can replicate right, entire B matrix on all the processes, right, and we can calculate the product, right, calculate the product. However, if we have small matrices, we probably would not go for parallelization in the first place. But let's say, depending on the problem, you may have to do several small B matrices, whereas the A matrix is large. Then you probably have to kind of go for some kind of a parallelization like this, where A and C will be decomposed row-wise, and entire B matrix will be made available on all processes. Okay, but however, this is not a really great parallelization technique because we are kind of replicating the data everywhere, so it requires a lot more memory on every process. Okay, so this is kind of not something that we would look forward to. So let us look at alternate methods. So second method is basically based on something that is we have already discussed, that is row-wise block decomposition. Okay, so we are going to basically look at matrix multiplication as such. So if you have to calculate Cij, then what we have seen is that we basically have to look at summation Aik Bkj for k going from 0 to whatever n minus 1, right? Or basically if you are going from 1 to n, so this is basically n and this is 1, right? So that means if you want to have row-wise block decomposition, that means we want to kind of group several rows together, right? That means we want to group several of these i's together and then decompose them. Then to calculate several rows of Ci would require not only the same rows of Ai but the entire matrix Bkj. But however, we can also look in a different way. Let's say if we do not have the entire matrix but we only have one portion of this one row of this matrix, okay, matrix B, instead of the full matrix we have only, let's say, one row here. Then what can we do? Then what can we do is basically you just of course needs to multiply the first element. Okay, we need to multiply the first element with the first element here, right? And then of course only the second element, when multiplied with this second element in the column here, would add to the sum to this particular value here. But rather what we can do is, if we have only one row, we could kind of multiply the first element here, right, with the first element in the B row, and then we could also multiply the same element, the I11 A11, with the second, the first row second column element, and so on. So we could multiply with all of these, right, because that will add to some kind of a partial sum, right, with that, because that will be towards a partial sum. And then we would think of a way in which this particular row will be exchanged with other processes, okay, and then a new row of B will be brought to this particular process. That means, let's say we have another B here. Now next we're going to kind of bring this B to process 0, in which what we can do is we could again multiply this particular element, right, with the of course we would not multiply with this, we would multiply the second element, that is this guy, okay, that means A12 with this guy, that is B21, and then add it to the partial sum here, okay, and so on. So, and then if you have this guy, would multiply it here and then add it to this sum, and so on. Okay, so that means, so if I were to repeat again this process, we would kind of calculate partial sums. Let us say we have the A matrix B matrix product, which would kind of give you C matrix, but then we want to only have a blockwise decomposition. So to begin with, every process has only access to certain number of rows. So we have done a blockwise decomposition. Okay, so I have kind of drawing a few rows here. Each color again represents several I rows. So let's say 5 or 6 rows are grouped into one color here. But then what we need to do is so initialize the entries of C to 0, okay, to begin with. So this is basically the initial. Then what we would do is we would just go about multiplying whatever value available in the first element, you multiply with this and you add it here, okay, and then you multiply the first element cross with the second element, and then you add it here, okay. Again you multiply this with the next value and then add it here, and then do the same thing for all the elements, okay. Then what happens is that then we would in some way basically send this particular row to another process. So let's say this, we send it to this row 1 to, let us say we send it to process n-1, okay. So this basically kind of comes down, and then this process comes to process 0, and this row comes to process 1, and so on. So basically we shift progressively all the rows up without changing the process decomposition for A or for C, okay. So for A and C there is no exchange of data, whereas only for B we push this guy to Pn-1 and we push P0 to or this P1, the red line presiding on process 1 to process 0. So that means what we need to do is on process 0 now the A12, so this element now will be multiplied with this element, and that would add to the partial sum of this element that is there. Again you would take A12 multiply with this guy, right, and then you add it to the existing partial sum and so on. So you would do that same thing, and then all the elements here now have contributions from 2 rows and 2 columns, right. So 2 rows and then the first column multiplication is gone into this particular row, okay, for all the columns of P, okay. Now what we need to do is, if we can exchange this now in basically n times or n-1 times, we can actually calculate all the partial sums, and that's it. And then we are done with the we will be done with the matrix multiplication, okay. So only thing is that here I have drawn all of them, but then in reality you would have each process will be holding one color code here, right. So that is the only memory we need to do, okay. So this kind of works fine if you have pretty much number of elements in the matrix is equal to, let's say, number of process. But in general you would have the number of process would be much smaller than the number of the problem size. So this is basically the number of processes, okay. So in such a case we have to so whatever I have presented here is basically for one row belonging to one process, okay. But then now if I say that, okay, each row, each color code here contains several rows here, okay, that means your number of processes much less than problem size, so we have to kind of group together several rows and assign it to one process, okay. So if we do that, then we have to come up with a way by which basically we could do the same problem but in a slightly different way, because now we have a group of rows being assigned to every process, okay. So let us now say that your ABC matrices are square, okay, for the sake of simplicity, and also assume that n is a multiple of P, okay, so that each process has a row that contains, each process contains n by P rows and n column values, right. So that means each process would hold a vector or a matrix of length n by P by n, right. Okay, so that's what we have. But then what we need to do is we need to so that means A, B, C to begin with will hold n by P times n elements, right. And what we need to also do is we need to also make provision for cycling n by P by n elements of B between processes, right, as part of the algorithm. Okay, so let us start the algorithm. That means initialize the np by n values of C to 0, and then what we need to do is during each process, let us say, let me kind of draw a slightly different diagram here, which would multiply instead of one row per process. Let me draw 2 rows being assigned to one process. Okay, let's say these are the elements that belong to process 0, and these are the elements that belong to process 0, and then these are the elements that belong to process 0. Okay, so that's what we have. Then basically the length here is n, here it is n by p. Okay, we have many other such rows being assigned to another process, okay, and so on. Okay, we are not worried about the red ones, we are worried about more about the black ones here to focus our attention. Then let's say there are 2 rows here, okay, and then here also there are 2 rows, and so on. Okay, so we have many here. Okay, we have many here. Okay, so essentially 2 rows here, and then n column values here. Okay, so this is 2 by n. Now how do we go about multiplication? We would multiply just like before. You would multiply this row with this column, right, and then you would store it here, right, and then you would go to the this row with the second column, and then you would store it here. Okay, similarly you would again take this and then go to the next column here. So multiply this row again with this column, right, and then you're going to get this value, and then similarly take this row and then multiply with the second column, right, and then essentially add it here. Okay, so do that way, and then essentially you would finish the same thing for all columns of B. You're going to get values here. Okay, so that is after initializing C to 0, you have gotten some partial sums here. Then what we would do is we would basically send this to process n-1 and then receive from process 1, receive into process 0 this red guy here. Okay, we would receive the red rows here, and then once the rows of red are received, then what we need to do is we need to move to the second block, right, and the second block, let's say, contains these elements. Now these elements now will be multiplied with these columns, right, these two, and then that will be used to update this value, right, and then the second row here will be multiplied with the first column, and then that's going to give you these values, right, these values, right. So essentially we would basically repeat the same process. Then you repeat it for all other elements here, all other columns, and then you're going to again on process 0 you're going to update all these values. So process 0 always holds these 2 rows, process 0 always holds these 2 rows of A and C, whereas the elements of B will be kind of cycled through, right, and then once all the cycling is done for all the blocks, we kind of finish our algorithm. Okay, that means what we have is so what we can do is, so in each iteration, so if I were to write basically in each iteration or in each step, every process multiplies n by p times n by p, right, block of A, right. So only this block of A will be multiplied by n by p by n, that is this entire thing of B, right, and basically updates the corresponding values in C, okay, in the portion of C. Okay, all right. So and then what we do is then we would kind of cycle the elements of B, and then the second n by p of A will be used to multiply the second row that is received. So we also need to kind of keep a track of what row we are multiplying with, right. So keep a track of the row that we are multiplying, right. All right. So if I were to draw a picture of how this kind of looks, so because for every process this is kind of fixed except for the elements of B. So if let's say if I focus on one particular process, process 0, we have, let's say this is matrix A, this is matrix B, and this is matrix C. Okay, so if I were to draw, then let's say this is to start with, what are the elements that process 0 holds. Okay, so this is A, B, and C, and what happens is that you multiply this and then you store it here. Then in the, so that is your basically the first iteration or step. Then you have the exchange, right? So how do you exchange? You send this guy to the last process here, and then you receive another block from the below, right? So that means in the second iteration, what we will have is we will have received, so the B elements received would have been from the second row, right? Oops. So let us say blue represents the second row, but this is not, this is owned by P1. Okay, so that would be received into P0. So what happens is that your B now on process 0 will hold this element here. Okay, and the red one would have been sent to P(n-1), right? If there are more other, I mean, of course other rows will be proportionately sent. So now you would again multiply them. So this is your second iteration, right? Now if I were to draw a third iteration, then let's say if you had a third row here, that would have been now become owned by process 0, and then essentially your other processes, let's say the red would have come here, and then now the original blue would have been sent to Pn-1 here. Okay, and so on. And then if we have one more row, okay, I think I'll just complete this picture. If I have one more row, so so this is the third iteration. So you would again multiply and of course add the corresponding values here, right, into C. So in every iteration, then finally we have let's say the fourth step, in which if we had one more row, 4 rows, let's say, or 4 blocks of rows, okay, that would have been that will be the top one here, then followed by the red one, followed by the blue, right, followed by the green. Okay, that's how it will be. And then again you would multiply with the orange in the fourth round, and then by then all the elements of C, let's say on process 0, and all other processes would have got the correct correct elements, right? You know, all the partial sum would have been computed. Okay, so if I were to again, let's say write these values for process B, so in the 4 iterations, how does the process B values look like? Okay, so this is basically matrix B values on every process. So it would be basically 0, 1, 2, 3 to start with, then it will be 1, 2, 3 and 0. So this is the first iteration, this is basically the second iteration, this is the third iteration, and this is the fourth one. So then it would have been 2, 3, 0, 1, and then you have 3, 0, 1, 2. Okay, so by then essentially all the elements can be easily computed, and then the matrix of elements of matrix C will be ready. Okay, all right. So so this algorithm is kind of nice because we have to basically only exchange or cycle rows of B between adjacent processes. Okay, and after each communication, new elements are received into B, and then of course we have to keep track of which block to multiply with depending on what is received, and then once you do, you would get the final matrix multiplication value. So this kind of is nice because it works well for large matrices as well. Okay, so this is kind of nice, but then there are a couple of caveats here. Okay, first thing is in terms of programming, we are now basically saying that we have to send and receive, right? So for example, let us say in the first iteration 0 will be sent to the process 3, and then 1 will be received into process 0, right? So that means we have to basically, if we talk about process 0 has to send it to Pn-1, and Pn-1 has to receive it, right? And then process 0 also has to receive from P1 its own row, so P1 has to send it, and then it has to be received by P0. Okay, so there is a one send and one receive by every process here, and similarly P1 will receive from P2 and it will send it to P0. So there is one send receive per process, right? That means we would basically have to send and receive n by p times n values of b after every iteration. Now you need to be a little careful when you try to write these send receive commands, because if you just use MPI send followed by MPI receive, and then this is how you would code it on for every process, then there may be a danger of hang up, because every process would see this, and then if this send happens to be a blocking send, it's going to block it until the message is received on the other process. And then what happens is that once all the process, that is P0, P1 all the way to Pn-1, if they come across this MPI send, then all of them would have sent and then will be waiting for some process to receive, and none of the process would actually receive it because all of them are busy sending it rather than receiving it. Okay, so if this happens to be a blocking send, then this may lead to some kind of a hang up. Okay, so as a result, you should kind of avoid such a situation. So what we can do to avoid such a situation is basically to rewrite the send and receive as two blocks. So the first block would be if let's say if my ID person2 equals 0. So if you are even, you basically first send and then receive. Okay, and then else if you happen to be odd process, then you can write it as you first receive, okay, and then send. So this way essentially process 2 would, if it sends it to 3 will be waiting to receive, and then it will kind of send, and then process 2 will receive, and so on. So as a result, this will kind of lead to a no deadlock, because now there is a pattern where all the even processes will send first and receive after that, whereas all odd processes will receive first and send later. Okay, so that is kind of the first thing you need to watch out. Now second thing is the buffer. Okay, so the buffer that you are sending would be the one row of B, right? This is basically n by p times n block of B will be sent, and also it is received. So as a result, you would need some kind of a temporary array which you can use either to send or to receive and store it temporarily on every process, so that the n by p by n would not be overwritten before it is sent by this process, right? So we have an MPI send here, right? So once we receive it, we should not kind of overwrite the B, because we won't be able to send the original values. Rather, this will become, all the rows will eventually become the same row if this is called several times. So when you receive it, you need to probably receive it to some kind of a temporary B array, and then the B needs to be sent, and then once that is sent, the B needs to be updated with this temporary values. Okay, so something like that needs to be done so that your B values are preserved, and end of the process, after A and B are completely multiplied, your B will still look like the original B. Okay, it will basically contain the original entries. Okay, it should not be B should be preserved. Okay, all right. So those are kind of couple of things you need to take care when you try to write this thing. Okay, so well, so far so good. This algorithm is kind of, the row-wise block decomposition is good, but there is one not so nice thing about it. It's basically the number of computations per element of B are kind of low. Okay, so as a result, the row wise block decomposition does not scale well as the problem size n is increased. Okay, so that means the thing is, because we are communicating this kind of a pattern of blocks, that those are basically n by p times n, essentially the number of computations we have per exchange of this is not very high. It's kind of very low. As a result, the computation to communication time is kind of low, or actually, because the communication takes some time to send and receive. As a result, it turns out that the number of computations per element of B are low, which will make it not scale as you increase the problem size. As you keep increasing n, this will not scale. So what is scale? So scaling means you would have probably got some kind of a idea about speed up. So the speed up you would expect as you increase your number of process and as you increase your n would not be maintained as expected from theoretical calculations. So that means it's not going to preserve that speed up, rather the speed up would kind of drop, which is kind of not good, because then we are wasting the resources because we are spending all the time in the communications. Okay, so as a result, we will look at another matrix multiplication algorithm, kind of with this motivation. We look at another matrix algorithm, which is basically depending on it's kind of based on an idea of checkerboard block decomposition of matrices. Okay, so using this, we're going to kind of devise another method of calculating matrix multiplication, which will have a better computations per number of elements of B, with which we can kind of, the algorithm kind of scales well. Okay, so that kind of leads us to the other method, that is checkerboard block decomposition of matrices, or also known as Cannon's algorithm for matrix multiplication. Okay, all right, so what do we need to do? Essentially, we have to somehow reduce this size of the B that is sent around, and so that the number of essentially the computation size will kind of come down, and the number of computations per element will kind of go up. Okay, so to do that, let us kind of take a look at matrix multiplication again. So what we have is, we have, let's say, matrix A, we have matrix B, which when multiplied kind of produces matrix C. Okay, so we have this, and we said that to calculate, let's say, one row of C, okay, I would use a color here. Okay, so essentially to calculate one row of C, we would need one row of A, and what we saw was we essentially need the entire B, right? We would need the entire B to calculate one row of C, right? So that is where the problem is. So, but let us say we don't want to calculate, we want to kind of pose our question differently. Okay, let us say we don't want to calculate, or per process we don't want to calculate entire row, rather we want to only calculate one, let's say, square or approximately square block of C. Okay, let's say we only want to calculate square block of C. Okay, we want to calculate some square block of C here. Okay, fine. That means then what we are saying is that we would need, for this square block of C to be calculated, we would need the corresponding row of A, right, as well as the corresponding row of B, right? So we would need whatever is depending on the block size. We would need only one row of A and one column of, or columns of B. That's all. We would not need the entire B matrix. So that is kind of posing the problem in a different way. Okay, so instead of, that means we want to go away from the 1D decomposition that we have used to essentially to a 2D decomposition. Right now, what we are saying is that we would like to only calculate elements of C that fall within this particular small square matrix as a submatrix of this big matrix. Let's say this kind of belongs to one particular process Pij. Then the elements we would need are only elements in that particular row of A and then particular column of B. Of course, again, now the decomposition is not is kind of 2D when you look at this thing, but we are going to find a way in which we can also make this particular decomposition also 2D, okay, such that we can calculate this easily. Okay, so then let us say we are doing a 2D decomposition of matrices A, B and C. Okay, let's assume that the matrices are of size n by n and we are doing a 2D decomposition. Okay, and because we are doing a 2D decomposition, if we assume that the number of processes is P processes, okay, let us assume that the number of processes per row and per column are square root P. So we have square root P times square root P in both X and Y or I and J directions, which would basically give you P processes altogether. Okay, that means the number of elements per process are of, let's say, A, B, C, of each of A, B, C, right? Are n by square root P times n by square root P. Okay, so let's say this matrix is of size n by square root P by n by square root P. Okay, and then of course each of these also will be decomposed into n by square root P, and we only want to store so many, and then we want to calculate entries of C with happen to be of this size of the submatrix. Okay, that's all this we need to calculate, and then we would only identify those rows and columns of A and B that are required to calculate only these elements, right? Okay, so that means we also of course have to make few assumptions in terms of the multiplicity of these things. For example, we assume that P is a square number, okay, and we also assume that n is a multiple of square root P, so that you basically get a another integer here. Okay, all right, so and then what we do is we say that the process kind of needs to reference n by square root B by n by square root P of C that needs to be calculated. Okay, so this is so far so good. So we are now decomposing our A and B using a 2D decomposition. Let us see if we can do that. So I'm going to represent, let us say, using 4 by 4. So I'm going to use an example of 16 processes. Okay, I'm going to draw submatrices, and each of these matrices now kind of belongs to one process. Okay, so each square block here is a process. Okay, they are supposed to be all equal. If they are not looking equal, then we just assume that they are equal. Okay, all right, so we have 16 by 16. All right, then I can go and say this is basically your, oops, I need to switch off this guy. Okay, so this is A00, B00 also holds by this. Of course, C00 also will be of the same size. I'm not writing it here. And then we go to second column, A01, B01, okay, A02, B02, A03, B03. Okay, similarly we have A10, B10, A20, B20, A30, B30, and then we have A11, B11, and so on. Okay, I'm not writing all of them. Okay, you could write them. So this is good. That means a particular process Pij now, instead of containing n by P by n size of A, it only contains n by square root P times n by square root P of A, B, and C. Okay, that's all. Okay, C is also there, which I did not write here. Alright, now what we see is that this seems to be fine, but the problem is here, except for the diagonal elements, except for the processes, on the main diagonal, okay, the other processes would not multiply their copies of A and B together, right? For example, if you look at it, basically to calculate the C00, A00 needs to be multiplied with B00 because that will add some kind of a partial sum in the calculation of C00, right? Similarly, A11 and B11 needs to be multiplied at some point to add a partial sum to C11, right? Similarly, A22 and B22 needs to be multiplied, and A33 and B33 needs to be multiplied. So all the elements along the diagonal, these can make use of their own copies of A and B to begin with, to multiply and then contribute to the partial sums of C, corresponding C calculations. Whereas in the calculation of let's say C01 submatrix, A01 will never be multiplied with B01, right? Because A01 will be multiplied with B10, not with B01, right? So this will never contribute to a product in C01. That means we cannot make use of this particular assignment of values to the processes to calculate C01 to begin with. Okay, so we need to kind of come up with a way in which we can move these blocks around, right, so that the corresponding multiplications can be done when they are exchanged. So if you go back to the matrix multiplication, we would be requiring row of A with column of B, right? That means if I go back, what I can say is that, okay, if there is a way I can make these blocks here, right, 4 blocks and then 4 blocks, okay, another block here, another block here, block here, then what we want to do is we want to arrange them, these guys, so the decomposition is basically now, so let's say this process and this process, let's say, belong to one particular this block and this block belong to one particular process. So we want to kind of move these blocks around in such a way that once we are done moving them, we will basically get all the partial sums that we wanted. Okay, so we want to kind of move them. So to begin with, one way to do this thing, there could be multiple ways, is to rearrange these blocks. For example, to begin with, what I want to do is I want to send except for the, let's say, I mean including the, let's say, the diagonal elements, we want to send the ith process would send its own matrix A to I process to the left, to I places to the left. For example, 1 would send it to 1 place to the left, 2 would send it to 2 places to the left, and 3 would send it to 3 places to the left, and so on for the A matrix. And similarly for the B matrix, we would like to send the jth process would send it to j places to the above, and so on. So for example, B to 2, let's say we would like to send this to 2 places to the up, and then every process would do the similar thing. For example, 3 would be sent it to 3 places to the up, and this one should be sent it to 1 place to the up, and so on. Okay, so what I want to do is I want to start off with another, so the initial arrangement of the blocks would be like this. Okay, so we want to send, let me write this basically, each process in row I of the mesh, of the, rather, you know, I can call it as processor mesh, right? Basically this is basically the process mesh, cycles its block, okay, its block of A to the process I places to the left, okay, to its left. All right, and each process J in column J of the processor mesh cycles its block of B to the process which is basically J places above it, right? Okay, let us see if we can do this. That means we want to move around, let's say, so the 0th process would not be affected because A 0 is in row 0, so it doesn't have to send it anywhere. So row 1, this will be sent to one process to its left. So basically this will become A11, this will become A22, A12, and this will become A13, and so on. Okay, so let me draw these again. Okay, that will be easy. Now I am kind of not drawing the square blocks, but I hope you would understand this thing. So let me draw this as A 00, right? What we have is A 00, B 00, we have A01, B 01, A02, B 02, A03, B 03, then we have A10, 11, B 12, sorry, it should be A12, A13, okay, then we have B10, B11, B12, B13, then we have A20, A21, A22, A23, B20, B21, B23, B22, B23. Okay, so that's 3 rows, and then we have A30, 31, 32, 33, B30, 31, 32, 33. Okay, so we have these blocks. We know that basically one particular process has this, another process has this, and so on, right? Okay, so we have 16 processes holding these things. Now we want to rearrange these using the algorithm we have said before. That means process row I of process A will send its block to I places to its left, and column J of process B of any process will send its block of B to B places above it. So 0, there will be no change, right? Because for A, row is 0, so there will be no change for A 00 because they all are on. So this will remain the same, A00, A03, right? I will come to B in a little while. So let me go to the other A's. So A10 needs to be sent into one place to its left. So it means A10 will go to the last process. So A11 would come here. So we'll have A11, A12, A13, and A10. That means it cycles its block of A by I places to its left. And then A20 happens to be the second row, so A22 would come to A20, right? This process would now have A22, right, followed by A23, followed by A20, then A21. Similarly, 3 needs to be cycled by 3 places, so A33 will come here, followed by A30, followed by A31, followed by A32. Okay, so that's what we have for the process I. For the blocks of A. Then for the blocks of B, we need to send them, depending on the column J, they have to be sent to J places above it. So again, for B, there will be no change for the first column because these are all in column 0. So this will be B20, B30, whereas block B here, B01 is in first column, so it needs to be sent by one column above it. That means it will come down. So that means B11 would come here, followed by B21, followed by B31, followed by B01. Okay, then here B02 needs to be sent by 2 places above it, so B02 will come here. So B22 would come here, followed by B32, followed by B02, followed by B12. Okay, similarly B33 would come by 3 places, so this will be B33, followed by B03, followed by B13, followed by B23. Okay, so that's what we have. All right. Okay, now what we see is that we have now obtained a rearrangement in which A00 and B00 can be multiplied together, because now whatever this process holds can be multiplied together to yield some value in C. Similarly, A01 can be multiplied with B11 because 1 and 1 match here. So this will also contribute to some partial sum towards the calculation of C. Similarly, A02 and B22 can be multiplied. Similarly, A03 can be multiplied. So essentially what we see is that now all the processes, right, can multiply their partial A and B matrices to calculate kind of partial sum towards C entries. Okay, so far so good. So now we have got one, but then now what we need to do? What we need to do is basically, as we have seen before, we have to rearrange these things, right? So now let's say A has been multiplied with one particular element, then this has to kind of go to its left and this has to kind of move up. So we have to kind of keep swapping this such that the rows will now move. So this is the initial arrangement that we propose, in which we can already multiply. Then all we have to do is then each process basically has to send its content irrespective of the row or column. Every process that holds a A needs to be sent towards its left, and every process that contains a B needs to send it to its one process above it and receive from one process below it. So basically, if we kind of set up a communication pattern like this, then by the end of square root P cycles, right, or iterations, we will have made all the A's and B's contacted each and every A and B, and then that would have resulted in the partial sums becoming the complete sum for C. Okay. So what we need to do is, if I draw this from the point of view of a process P12, let's say from the point of view of P12, then we just need to cycle after the initial arrangement. Every process needs to cycle its component of A towards its left process and receive from its right process, and every process that holds a B needs to send it to one process above it and receive one from the below. Okay, so we need to kind of make this arrangement. So for example, and if we do that for square root P times, then we have made all the B's and A talk to each other, and that would have resulted in the complete sum of C on every process. So from the point of view of P12, let me draw here. So basically we have let's say 1, 2, 3, 4, one above it, one below it. So I'm kind of focusing on P12. Okay, that's basically the 0 is the first row, this is the 0th row, and then first row, and then we have 0, 1, 2. So this is process P12, and to begin with we have basically A11, A12, A13, A10, right? Then we have B22, B32, and then B02, and then B12. Okay, so we would multiply. Then this is the original thing we have already have here, right? So this is A13, B8, B32. So this is the initial arrangement. So here we would multiply them together. Then once we do that, process 0 on process 0, A will send it to A12 and then receive A10 in the next step, right? Similarly, this guy will send here, B will be sent here, and B02 will be received into B32, and B32 will be sent to B22, right? This is basically another process. And then similarly B12 will go up, and then this B22 will be received here. Similarly A10 will be received here. Okay. Oh, sorry, A10 will be A11 will be received into A10, and A10 will be sent to the process before it. Okay, so this is not correct. Okay, so that is one cycle. Then in the next iteration, what we have is if I draw the process again, 1, 2, 3, 4. We have 1, 2, 3. Okay, so we would have received. So this process would have hold a copy of A12. This would be A13. This would be A10, and this would be A11. Similarly, this would be B32, right? And then this would be B02, and then this will be B12, and then this would be B22. Okay, so that means again we got A10 needs to be multiplied with B02 on process 1, 2, and so on. So we again, after this, these A's will be shifted in a row to its left and receive from right, and B will be shifted up and receive from bottom. Okay, after this we have 2 more iterations left. which will kind of compute or finish all the computations or all the calculations in C. Okay. Now summing all these partial results on every process, all these results on every process would produce the matrix multiplication for C. Okay, basically, and it will basically give you the elements of correct elements in C1, 2. Okay. All right. So that's about the matrix multiplication using Cannon's algorithm, and this particular algorithm seems to have a high value of number of computations per element of B. So as a result, this is kind of scales well compared to the row-wise block decomposition, but row-wise block decomposition also might work for kind of scale well for a certain number of process and problem sizes. Okay. All right. So what did we plan for today? We planned for matrix addition, multiplication, explicit finite differences, and then we kind of seem to be out of time with this. So what I'm going to do is I'm going to kind of stop here with the matrix multiplication, and we'll pick up with the explicit finite differences in the next lecture. Okay, thank you. Talk to you in the next lecture.